nanopores. Then he began his professional career as a postdoc working at the Neutron Scattering Center at Los Alamos National Laboratory, and he has been the co-instrument scientist of the spectrometer for materials research at temperature and stress called Wisely SMART since the commissioning of it in 2003. SMART was actually the first neutron scattering instrument designed for the study of engineering materials and is based on the philosophy of studying materials' response to conditions simulating operating and or processing, and it's been the first of its kind. Don has extended this broad philosophy to include large-scale X-ray scattering facilities such as the Advanced Photon Source at Argonne National Lab. He's been focusing quite a bit of his research on nuclear weapons and energy materials, but also has been doing work on aerospace, automotive, and functional materials as well. And most recently, his research has included in situ processing and performance of additive manufactured materials. He's senior scientist at Los Alamos and team leader of the materials scattering group in the material science and technology divisions. He has more than 250 publications and an amazing aging list of 42. But no further ado, the stage is yours. Thank you, Don, for being with us.
Thank you for the introduction and the invitation to be here. I really appreciate it. And Diana said, just point this down a little bit. She said I was world renowned in my field. That means like 6 people know who I am. So I'm going to talk today. It'll be both neutron and energy and X-ray scattering, looking at manufacturing. Manufacturing is pretty highly interesting at Los Alamos National Lab right now for reasons that you can guess. I won't go into those reasons a lot. I'll go into them a little bit. And by the way, if I go into your lunchtime, it's not my fault. Sorry. I will go into your lunchtime stuff. I'll try to get us back to the time schedule. Find something that will advance. There we go. Okay, so Los Alamos National Lab. So the interesting thing about Los Alamos is we have a distinct mission, right? So a university or even some of the other national labs, maybe their mission isn't so well defined, but Los Alamos very much has a mission. That number one mission is to keep our nuclear stockpile deterrent, operable and functioning and safe and all those sorts of things. So we have a goal in the research that we do, and that drives certain things. And you can sum up our mission. This is the way it was summed up to me when I was a new staff member. So you should all be aware we don't test our nuclear weapons. We haven't for 30 or 40 years. So you can think of this as having an F1 race car. These aren't Ford Pintos that we have out in the desert of Arizona or Texas. These are cutting edge, high technology when they were built components. So taking an F1 race car, keeping it in running shape without turning the key and starting it. And it's been sitting in the garage for 50 or 60 years, and you need to have confidence. Every year, the director of Los Alamos National Lab signs a letter to the President of the United States saying, I certify if you turn the key to this race car, it'll run. Right? That's our mission at Los Alamos, is making our director have the confidence that he can write that letter to the President of the United States every year. It's a very serious mission, and we take it with appropriate seriousness. So that's the deterrence and stockpile stewardship, protecting against nuclear threats, right? So we have lots of adversaries out there, and that's part of our job, is understanding their threats and how to protect against them. Emerging threats and opportunities, right? Lots of things change. New technologies come out. In fact, new technologies come out now faster than ever. So trying to be ahead of our adversaries is one of the reasons we do science. We want to do the science before they do it so we can learn how to respond. And Los Alamos has certainly, in recent years, taken energy security, and this is more prevalent than ever, right? With Russia threatening, or not threatening, but turning off gas pipelines to Europe, it's becoming more important than ever to control our own energy supply. And we take that as a security mission. So in all of these types of mission space, materials problems absolutely pervade, right? So materials science at Los Alamos is a very important part of our core competencies. Well, that means that recently additive manufacture has certainly been interesting thing at Los Alamos. And to be honest, manufacture as a whole is very interesting, but in the broader world right now, additive is a very buzzword, if you will, in material science communities. So where it matters for Los Alamos' mission is, certainly AM enables the production of small lot quantities, right? GE has that little fuel pump thing, they make 1 billion of them, right? That's a different need than what Los Alamos has, right? If Los Alamos ever did do a large run on additively manufactured components, it might be a couple thousand components at the most. It might be one, right? Or it might be 5. So additive actually gives you that ability to stand up production of small lots of components. It allows you to be responsive and agile. You don't have to create a whole new rolling, forming, heat treating, annealing, machining process in order to make a component. You just put a new design into the machine and it spits out the part. It reduces the amount of waste. A lot of the materials we use at Los Alamos that are either expensive, exotic, or they're nasty things to go throw in the trash. So reducing how much of it you use in order to make a component is important. It reduces manufacturing footprint. If you follow these sorts of things, you'll know that the most recent proposal to build a uranium foundry in Tennessee is a $2 billion facility in order to build the components that we need. If we could make those other ways without building a huge facility, that's important. And finally, it can add functionality, right? You can print a lattice structure that gives you the ability to control the weight to stiffness ratio in a way that you can't just by material selection. So there's lots of things within additive manufacture that get Los Alamos' interest. Of course, additive manufacture comes with problems, right? Those of us that are familiar with AM have seen things like that before. When you grow a part with AM, you can get cracks in it while it grows. It can fracture just from the residual stresses. How to control those residual stresses is the material science problem. On the other end of it, you often, if you are successful in growing it, you get components that have different properties than you might expect. Same part from a normal casting and forging operation. What I'm showing you here is just plain old tensile stress strain curves from titanium. The dashed line is if you make it in a traditional way, cast it and then roll it. The solid lines are all different additive manufacture processes. As is quite often the case, you get very different properties. In this case, it's 30% stronger in the AM material. And that again gets down to material science and how the microstructure is different due to additive manufacturing. And that's really going to be the basis of my talk, is trying to understand how different manufacturing procedures or processes can affect performance. And that's this slide, which is shamelessly stolen from Rusty Gray. I want to give him credit because he gets angry at me. He probably still gets angry at me, but at least if I give him credit, I feel better about it. So potato chips, right? 3 kinds up here: kettle cooked, Ruffles, and Pringles, all made with the same basic ingredients, right? If you look at the ingredients, any of those will have the same basic ingredients. They all have different processes in how they make them. And because of that, you get different properties. They taste different, they have different texture. So this is just a silly little example of process structure property relationships, right? Metals are very much the same thing. I'm showing you here an example of beryllium. Beryllium is typically made by powder pressing techniques. On the left is a microstructure from just hot pressed beryllium powder. You have equiaxed grains. They're all about the same size. They're isotropic. If you look at wrought beryllium, beryllium that's been rolled, now your grains are flattened out like pancakes. So here you have the same ingredients going in, but you have different structure, right, that comes from the process, and that results in different properties. On the left are stress strain curves as a function of strain rate for the hot pressed beryllium. On the right is the rolled beryllium, and you see it's a factor of 2 stronger in the rolled material, right? So that's the process taking the same ingredients and giving a different structure, which results in different properties. In material science, we call that the process structure property relationship. Where I sit, and because I sit in the material science and technology division, I'm contractually obligated to show the materials tetrahedron at every talk I give. Our team, the material scattering team, sits squarely on structure. And by structure, I mean microstructure now. We use diffraction, imaging, other scattering techniques in order to characterize the microstructure, which is the linkage between the processing and the properties and eventually the performance. Because at least at Los Alamos, what it really comes down to is performance. So we use diffraction. So I've shown you here an example of a diffraction pattern. You can pull out different quantities from the diffraction pattern. Things like the peak position tells you how far the atoms are separated. The intensity tells you things like phase fraction and stuff like that. The peak width gives you information. But we take all of that, and this is one of the things I'll kind of preach on a little bit today. Parameters for diffraction patterns are meaningless, right? Telling somebody that a peak has a certain intensity doesn't mean anything for material scientists. What matters are microstructural features. So we want to be able to pull out things quantitatively with uncertainties like phase, defect concentration, dislocation densities, texture matters, right? Internal stresses, solute chemistry. These are all things, if you're careful and you do the measurement right, you can get out of the diffraction pattern. And that's, again, that's our job. We try to understand how processing affects structure and that impacts properties by pulling out microstructural features using diffraction. The nice thing about neutron and more recently high energy X-ray diffraction is it gives you that window onto the microstructure non-destructively. So I can look at a material as it's actually performing, right? I can do a tensile test and take diffraction while the tensile test is happening and watch how the microstructure is responding to that environment. And that's what our team does. In a perfect world, we're providing that data to modelers, right? If we do our job and we're just doing an experiment just for the experiment's sake, that's not very interesting and not very productive. If somebody, say a student at WPI, says, hey, I really need to know the vanadium content in beta titanium as it phase separates. If we can give that data to a modeler and they successfully turn that into a model, then we've done a lot more than just making a plot of vanadium content in the beta as a function of time. And that's really what our goal is, to provide data to modelers, to theorists, in order for them either to develop their model or to validate the model. That's when we do our job well, that's what we do. Now, there's a problem with using diffraction to pull out microstructural feature, and that's, I just showed you 3 different things you can essentially pull out of a diffraction pattern, and there's about 900 things in the microstructure that can affect those 3 different things. And how you deconvolute those effects are what take you from, okay, interesting idea to, okay, that really impacts material science. So the simplest one is the spacing between the atoms, right? We use diffraction to measure the spacing between atoms very accurately to about 10 parts per million. Think about that. That means we're measuring the spacing between atoms to femtometer accuracy, okay? And it's actually not that hard to do. But how do you interpret that? Because there's a lot of things that can change. Certainly temperature, right? If you're doing annealing in situ, you raise the temperature, that changes the spacing between atoms. It'll also change the solute chemistry, and the solute chemistry changes the spacing between atoms. Stress will change the spacing between atoms, right? If you squeeze something, the atoms get closer together. That makes sense. And that even has sub areas that are convoluted within it. You have type 1, type 2, and type 3 stresses, macroscopic stresses, intergranular stresses, and intragranular stresses. Those all affect the atomic spacing. So how do you deconvolute all those effects out of the diffraction pattern? That is what a lot of what I'll talk about is today. If you go into some of the other features, like, oh yeah, that's, forget it. The peak intensity, same thing. Phase fraction will affect the peak intensity. Preferred orientation will affect the peak intensity. One a lot of people ignore is the Debye-Waller factor. If you change the temperature, that will affect the peak intensity. Those things, again, are all convoluted. If you go into peak width, this is where things really get hairy. A lot of times, people will interpret peak width in terms of microstructural features like dislocation density, like coherent crystallite size, but there are a lot of things that can affect peak width. And if there's no other message that I get across today, especially to students, is that make sure you think about how you interpret your data, because there are a lot of things that could be convoluted in with that. Lunar phase affects peak width, I think, sometimes. So how do we do that? Again, I think I said the peak spacing is the easiest one to sort of deconvolute in my mind. So if you think about diffraction, when you do diffraction, you get out the Debye-Shearer cone of diffraction. And when you're trying to determine the interatomic spacing, what you're doing is measuring the radius of that cone. Okay, so this is supposed to be a schematic picture of the Debye-Shearer cone as it intersects the computer screen. In this case, it's a perfect circle. It's supposed to be a perfect circle if the projector is on. So that's nice and simple. If you change temperature, still nice and simple. Temperature is a scalar, so it changes your Debye-Shearer cone in a symmetric way. The radius gets bigger as the temperature gets smaller. It's an inverse relationship. Okay, so temperature has a relatively simple effect on the interatomic spacing on what you actually observe, which is the radius of the Debye-Shearer cone. Unfortunately, solute chemistry has the exact same effect. Now, this can get a little bit more complicated if you think of second order interactions, but in terms of first order, if you change the chemistry, if you change the amount of vanadium in solution in Ti-6,4, you just change the radius of that Debye-Scherrer cone. So it's hard to segregate chemistry from temperature if you don't know anything else a priori. You usually have to know something else, like measure the temperature a different way. Stress, however, gives you a different effect, right? Stress is a tensor. So if I pull on my sample this way, the atoms get further apart this way. That means the Debye-Scherrer cone actually gets smaller in that direction, and it gets larger in the other direction because of the Poisson ratio effect. So that's an effect that I can separate from temperature or chemistry because it's a tensor effect where temperature is a scalar effect, right? So if I measure the full Debye-Scherrer cone or enough of it, I can separate the effect of temperature from the effect of stress. So if I'm annealing something, I can tell the difference between thermal expansion and stress relief, for instance, and you'll see that example, I think. Now, a shear stress actually is a little different, where a uniaxial stress turns it into an ellipse. The shear stress rotates that ellipse. Okay, it rotates the major and minor axes. So again, those are things that I can separate out. So these are all the things that go into when I make a measure of lattice parameter. I consider all these things when I interpret it from lattice parameter, which is not very useful, to internal stress, which is something that's useful. And that's the case for all microstructure features that we're going to pull out. There's everything I just said written down. Okay, so I sit at Los Alamos Neutron Science Center. So I went to Los Alamos specifically because I wanted to be an instrument scientist at one of these types of facilities. And Los Alamos Neutron Science Center was a good choice for that. What it is a proton beam that's about 2/3 of a mile long or something like that. So it's a proton beam that's accelerated to 800 MeV. We take that proton beam and we use it for lots of things on the way, and I won't go into details. Where we sit is down here at the end of it, the neutron scattering center. That proton beam, we slam it into a tungsten target, and it hits the tungsten nuclei hard enough that it literally blows them into pieces. It's called a spallation reaction. It takes those nuclei and turns them into their base protons and neutrons that go flying out, and we collect those neutrons and use them for scattering experiments. That's as much as you really need to know, but that's where we do some of our work. Is we use neutron diffraction to do the sorts of things I'm talking about. Neutrons aren't perfect, aren't the right tool for everything. We also use X-ray diffraction sometimes, but not, this isn't your grandfather's X-ray machine sitting on a bench top in the lab down the street, electrons hitting a copper K alpha target, giving off X-rays. Those are 8 kiloelectron volt X-rays. They penetrate a few microns into most metals. We use facilities like the Advanced Photon Source just outside of Chicago, or CHESS up at Cornell, not too far from here, where they produce X-rays in a synchrotron. Again, this is about a mile in diameter circumference. The beamline that we use produces X-rays up to 100 kiloelectron volts. At that energy level now, I can start to penetrate macroscopic amounts of metal. I can penetrate 2 centimeters of titanium, for instance, with a 100 kilovolt electron or X-ray beam. I can penetrate 0.5 millimeter of uranium, which gets us into the area of interest for Los Alamos. So the technique that the probe particle that we tend to use depends a lot on the problem we're trying to solve. It depends on the kinetics of what we care about. Neutrons are inherently slow. You only get so many neutrons out. It's limited by heat flow and things like that. You don't need to worry about that. The neutron measurements in general are slow. They look at bulk amounts of material. My neutron beam might be anywhere from a couple millimeters big to a centimeter big. So I'm looking at cubic centimeters of material and averaging over all of the grains in that cubic centimeter. So one of the things neutrons give you very well is averaging over, gives you a nice statistical average of all the grains. One of the things it doesn't give you is spatial or time resolution. A measurement at the neutron beam will take me anywhere from a minute to an hour. Dan, his neutron beam might do a few down in a couple seconds range, but that's about as fast as we're going to go with neutrons. X-rays, on the other hand, at the APS and CHESS, are advancing in terms of the flux and brilliance of X-rays, are advancing at a rate that's unbelievable, and I won't go into the details, but it allows you to do things that neutrons just can't. You can get sub-millimeter resolution, micron type resolution, spatial resolution with X-ray beams. You can get sub-second resolution. There are places like the linear coherent light source that use X-ray lasers to get femtosecond or tens of femtosecond time resolution. So if you're looking at something like an exploding component, you can get an image in tens of femtoseconds with those types of X-ray things. The problem is you get much less grain statistics. So if you're trying to do, if you're trying to relate it to macroscopic plasticity, that's often hard if you're only seeing 1 or 2 grains, because grains can be outliers and things like that. Point is being here, the rest of my talk, I will talk about X-ray and neutron. It doesn't really matter which one I'm talking about. How you interpret the data in terms of microstructure is very similar. How you choose your probe depends on the problem you're doing. You're doing something slow and a big component, then you use neutrons. You're doing something fast and a small component, then you use X-rays. There's a little bit more that goes into it, but that's 90% of that decision tree. So the first example I'm going to give you is in situ wire arc additive manufacturing. This was done at the Advanced Photon Source, and this is the actual process going on. So what we have there is a wheel that's rotating, and as it rotates, we're depositing material on that, and we're passing X-rays basically right along into the screen. We pass X-rays through that depositing material, and we collect diffraction data while it's solidifying and cooling, and we can pull out microstructural features while that's happening. Here's a better movie. Maybe it won't be a better movie because it's not bringing up the bar. Well, you can kind of see here, this was a movie, but what you're seeing here is a droplet of material that's coming from a wire arc, right? So there's a wire above here that you can't see it. It creates an arc, material flies off that arc, just like a TIG welder or a MIG welder, if you want. And that droplet of material lands down on the plate and it starts to grow a bubble, right? This is how welding works. It's how wire arc additive manufacturing works. And while this is happening, we're passing X-rays through that bubble, which is the glowing part. It doesn't look like a bubble now because it's wiggling, because it's liquid. And we'll see the liquid and we'll watch that as it solidifies, and we'll watch the texture and the phase transformation. This is 316L, I'm sorry, it's 304L stainless steel. So it'll transform, it solidifies in the austenite and it transforms to the ferrite. And we're going to attempt to watch all of that happen with the X-ray beam and pull out microstructural feature as it does happen. This is a schematic of the instrument. So from the left, you have the X-ray beam coming. It was about a 70 kilo electron volt X-ray beam. So it'll penetrate the 3 millimeter drop of steel that we have on there. It penetrates it easily. Because it's such a high energy X-ray beam, the wavelength is very short. If you remember Bragg's law, as the wavelength gets small, the angle of scattering gets small, right? So the scattering angle is actually about 2 or 3 to 5-ish degrees, the Bragg angle. So this is actually the Debye shearer cones that I referred to here. So we actually measure about 5 different Debye shearer cones for each phase that's in the austenite, or I'm sorry, in the stainless steel. So the austenite, the ferrite, we'll see 5 different HKLs, 5 different peaks from each phase. And that gives us enough information to determine phase fraction and separate phase fraction from texture and things like that, and Debye-Waller factor to a degree. So the way we analyze the data, because as I said, I want to separate a scalar effect, which is temperature, from a tensor effect, which is stress. So we take these rings, and the first thing we'll do is integrate all 360 degrees about the angle eta that I've defined on that picture. And that gives us the average lattice parameter, and that's what's related to the temperature. And you can go through the mathematics, I won't do that here. Then we break up that ring into 24 15-degree increments, call that caking. It's because the program was written by an English guy. It was written by an American guy, it'd be called PIE, which is a lot harder to say than caking. But anyways, we cake it into 15-degree intervals, and then we get a lattice parameter as a function of angle, and that's what gives us the tensor part, the stress. Okay, so that's how we separate those things. And we do similar things to separate phase fractions, how the phase fraction affects intensity from how texture affects intensity. I'm not going to go into details of that. So if you think about the strain and how that lattice parameter measurement happens, if you take the strain tensor, which is on the top left, right, there's 6 independent components on there. You can separate that into a hydrostatic part and a deviatoric part. And if you do the math, if you calculate a strain from the deviatoric part, so here you basically subtract out the average lattice parameter, you see that the deviatoric part becomes relatively insensitive to the reference lattice parameter. And that's where one of our problems always is how do you measure a reference lattice parameter? Because it's just hard to get. So by subtracting out the average the way I've done here, you get the deviatoric strain is only linearly related to the reference lattice parameter A0. Well, that only changes a little bit. So a proportionality there isn't a big deal in the uncertainty. The problem comes in the hydrostatic portion, which is here. Now you're doing a subtraction between the average lattice parameter and the reference. That difference in itself is very small. So if you're uncertain on A0, A0, the reference lattice parameter, when you take a subtraction, that uncertainty becomes very important, right? When you're just doing division by A0, it's not so important because it's just linearly related. But when you're subtracting two things that are very close, that becomes actually a dynamic or a driving problem in your uncertainty. Well, not only is it separable mathematically like this, but it's also separable in terms of physics. And we've talked about this. The deviatoric strain is all of the orientation dependent part, right? So that's where all the mechanical strains show up, stress. The hydrostatic strain is the temperature and chemistry. So you can separate it both mathematically and in terms of interpretation. And that's what lets us pull out microstructural features from an effect that's pretty convoluted. So here's one of those little droplets that we deposited in situ at the X-ray beam. We collected data. I have the three little squares there, blue, red, and green. So these were all collected on different droplets, but they were collected at different heights relative to the base plate. So we could look at how that affected, for instance, the transformation rate from ferrite to austenite, from liquid to solid. This deposition took 1 second. So we basically turned on the welder for a second. It put down this little 3 millimeter, well, we call it a cow patty. You can imagine why we did that. But this little 3 millimeter point deposition, if you want. And while that was cooling, we're collecting data. Now, when we did this measurement in 2017 or so, the fastest detector could only read at about a 10 hertz rate. So that was limiting on how fast we could collect data. And when we did these experiments, more than really trying to understand stainless steel, we were trying to understand the technique and how far you could push the technique. Okay, so collecting data every 1 second, you can see the austenite fraction that I'm showing there as a function of time. We really only get 1, maybe 2 data points before the reaction is complete. So the conclusion from here, remember, we're trying to evaluate the technique. That is, in 2017, we weren't ready to take on the ferrite to austenite phase transformation as it quenched because it happened faster than our fastest detector could keep up with it. Okay, so we had to come up with a solution for that because the data wasn't just fast enough. Well, here's an example where we actually were fast, probably fast enough. So this is looking at the lattice parameter as a function of time. So not the phase fraction, but the lattice parameter. And you can see that it drops, right? That's just thermal expansion. But also notice that I'm showing you here the average in the thick black and the orientation dependent lattice parameter. So again, this is the difference between the radius of that device shear cone and the eccentricity of that device shear cone. That spread in lattice parameter as you get out to long time isn't random. That's not uncertainty. If you look at it at 0 degrees, the red is up high. At 90 degrees, that's is low. So at 90 degrees is, if this is the base plate, 90 degrees is normal to the base plate, 0 is parallel. What you're seeing there is the residual stress develop as it cools. As it cools, it tries to contract. In the plane of the base plate, it doesn't want to let it contract. It's constrained. So the lattice parameter is actually stretched. So at 0 degrees, the lattice parameter is bigger than the average. At 90 degrees, it's smaller, again, because of the Poisson strain effects. It's actually unconstrained in the vertical direction. So the average of that tells us the temperature. The spread of it and the nature of that spread tells us how the internal stress is developing as this liquid solidifies and cools. Oh, that's not good news. Oh, I have an hour. Oh, it's not showing that. It's good that it's not showing up there. I just got a message that my laptop's going to restart in 59 minutes. So we're okay. Hopefully I won't talk that long. Although if you're interested, I'm happy to. Oh, so if you blow that up a little bit, so if you blow that spread up a little bit, you can see better the orientation dependence. So we get the temperature and we get the stress out of this as it develops. And we actually are getting enough temperature points. Our time resolution is sufficient to measure temperature as a function of time as it quenches. and then take the derivative of that, we can actually get cooling rate as a function of time. And that's important because it's the cooling rate that tells you how the chemicals segregate as you go through the liquid to solid phase transformation. So wire arc additive manufacture cools at about 1,000 degrees per second, which is, if you read the literature 10 years ago, that's kind of the estimate that you would expect. These are one of the first really internal, possibly the first internal measurement of what that temperature cooling rate is. Let's get through this in the interest of time. So as I said, the kinetics of the experiment we're doing here were actually still too fast for our measurement technique in 2017. That's actually changed. Detector technology is exploding because the X-ray fluxes are driving the detector technology because they're so fast now. So if you did this measurement now, the detectors can measure at sort of 250 to 500 hertz, where we were looking at 10 hertz 4 or 5 years ago. So what I'm going to say isn't necessarily true, but there's always faster kinetics, so it's still relevant. Point is, when we did these measurements, our detector wasn't fast enough. So we had to come up with a way to slow down the kinetics. So it's two things we did. So instead of just depositing a point of material and then turn the welder off so it cooled very quickly, we rotate that wheel and we deposit a line of material, doing actual additive manufacture, if you want to look at it that way. That, because you're continuously putting heat in, that greatly slows down the cooling rate. But what it also does is sets up a quasi-steady static situation at the point where the melt pool is, right? Because as you're depositing material and it's solidifying, it's being moved away by the rotating wheel that you're depositing it on. So after the first some amount of time that's transient, you set up a quasi-steady state. And that's true as long as you're integrating at a long time relative to the wire motion, which we are. So we're actually going to integrate for a second on here. That little red dot that I show up there, that's the size of the beam relative. That's kind of drawn to scale. So the wheel is 7 millimeters diameter. That's the blue bottom part. That's the base plate we're depositing onto. The gray stuff on top is the amount of material we're depositing. That's about 3 millimeters tall. And that little red square is 50 micron beam. That's the amount of material that we're integrating on or over as we count the data. That red line is the wire coming in, and schematically supposed to show it melting there at the origin. So I'll show you things, data as a function of position as you move away from the melt pool. And what we're doing here, to borrow a term from fluid dynamics, which WPI will understand a lot better than I do, is we're measuring in the Eulerian reference frame, right? You can think of this in terms of fluid flow as particles flowing past what we're measuring, and we're integrating through those particles as they flow past, as opposed to a Lagrangian reference frame. So what that means is as we move, well, I'll just move on now because the movie started. So this is a bunch of diffraction patterns that we collect during a well. So there's liquid, you see the broad rings, and there you see the sharp rings, that's solid. You see coexistence of liquid and solid, and now it's fully solidified. You see the rings, but they're not complete rings. And if you look closely, you'll see there's symmetry to the rings. That's the crystallographic texture. As it solidifies, certain grain orientations are preferred, right? There's a crystal growth direction, and that shows up in how the intensity varies as you go around those rings. So we can see the phase transformation from liquid to solid. It happened too quick for you to see in the movie, but you can see the change from ferrite to austenite. You can see the texture evolve. We can see the stress develop. Those are all microstructural features that we pull out of the data that you just saw there. So this is, more normal EBSD that you would see. This is a section of the of that line of metal that we laid down, and that the white shading on that line is where our X-ray beam was penetrating when we laid this material down. So that's our integration volume. If you take those rings and do a polar transform, turn them into rectilinear coordinates. On the far left, you see liquid, right? It's a nice broad diffraction beam. That's right at the melt pool. As you come further to the right, you're moving further and further from the melt pool. In some sense, you're moving back in time. You're seeing material where it's been longer since it's solidified. Okay, so you can think about it in either way. Again, now the spacing as you go down, the way the bright spots are, that's the texture showing up. So instead of being around the circle, now they're in lines. And it might be hard to see from your seats, but I've indexed the two different phases in stainless steel, the austenite and the ferrite. Stainless steel, or I should be careful. 304L stainless steel is a ferrite former. It solidifies as ferrite and then transforms to austenite. If you talk to welders, that's really important. That's everything in welding steel. If it forms as austenite and then turns to ferrite, then it'll fracture. So that's why you actually control the temperature in this steel, is to make sure it forms as ferrite first and then transforms to austenite. If you take those diffraction patterns on the left and integrate them vertically over that angle eta, you get what we're used to seeing as diffraction. On the top is again the liquid. Those broad peaks are the liquid scattering. If you go a millimeter away from the melt pool, you can now see, and the red dotted line is just a copy of the liquid scattering and translated downward. So the sharp peaks of the diffraction, the two sharp peaks up here, this peak is austenite, this peak is Fahrenheit. Okay, so it's more complicated than that, but we'll get the fractions of the austenite and ferrite by the ratios of those and the other peaks. But as you come down, you can see how we get less and less broad scattering. So you're getting less and less amount of liquid as you move away from the melt pool. And you can also see those two peaks that I pointed out are almost the same intensity at the start. As you move down, and this is on a log scale, so it's a little bit muted. But as you move down, you see that the peak on the right here becomes stronger than the peak on the left. Well, this is the austenite, that's the ferrite. So what you're seeing is the phase transformation from ferrite to austenite as the relative amount of those two peaks change. So now, because we've slowed down the system and because we turned it into a quasi-steady state, now we can pull out data on relative time and length scales. So you can look, for instance, as a function of distance from the wire, distance from the weld pool if you want, the temperature. So the dotted lines represent, depending exactly on the chemistry, the melt point of 304L stainless steel. And this isn't forced. We actually, by measuring the lattice parameter and knowing the thermal expansion of austenite, we calculate the temperature. It comes right at, it solidifies at the melt point. That's what it should do. It drops down, and at 9 seconds or so, that's when we turned off the welder. So now it starts cooling more quickly, but it's not rotating anymore. So now it's just time that changes. So you can see the temperature drop as distance from the weld. And then again, we turn it off and you see it quench because you're not adding any more heat. We did it at two different deposition rates if you want, and they actually fall quite close together. They're a little bit different. They go in the direction you would expect. So now we can pull out the temperature as a function of time. We can pull out the liquid solid fraction. So it starts out as purely liquid. It drops pretty quickly. And again, we're not quite fast enough to measure liquid to solid. Liquid solid happens really fast. We get 1 or 2 data points in the interim. But then it's sort of slowly, it's mushy zone. We really don't believe there's any liquid out there at 5 millimeters from the wire. That's certainly not true. But anyways, you can turn the amount of, you can then break the solid up into the amount that's ferrite, the amount that's austenite. So this in red is the fraction of the steel, the stainless steel that's austenite. You see it goes, and it takes about 2 millimeters of travel from the melt pool until it's pretty much its steady state amount of austenite. In the end, you'll find there's about 4 or 5 or 6% ferrite in there. That now, how the austenite forms as a function of temperature, because we have both sets of data. So here you're looking at the solid-solid phase transformation. 1 millimeter is how far we were away from the base plate. So you can look at that as a function of distance, and it turns out it doesn't matter. The cooling rates are different as a function of distance from the base plate, but the temperature at which austenite transforms to ferrite is not. And if you compare by LD, I'm talking about line deposition, PD is point deposition. Remember, the point deposition, the cooling rate was about an order of magnitude faster. It was 1,000 degrees per second, 1,500 actually. In the line deposition, it was more like 100 degrees per second because we keep dumping in heat, right? Turns out the rate at which the austenite transforms, or not the rate, the temperature at which austenite transforms to ferrite is independent of the rate over that 1 order of magnitude. Now, if you changed it to, 1 million per second, which is powder bed fusion, or a degree an hour, which is casting, that conclusion might change. But over this range, this relatively small range of cooling rates, the temperature at which austenite transforms, at which ferrite transforms to austenite is independent of the rate. And it's fit by an exponential equation. So you can pull out stress. What I'm showing on the top is, again, that's essentially the eccentricity of the lattice parameter. So the average would go through the middle of all that, but you have the Debye-Scherrer cone as an ellipse. You can pull, it turns out, because you don't, well, for various reasons, you can't pull out any component of stress. We don't have enough data. But what it comes down to is we only measure in one plane, right? In order to get a full tensor, you have to be able to measure in 3 dimensions, and we can only measure in 2. What I can do, though, is if I find the von Mises stress, and it's because all of these subtraction terms, a lot of things fall out, I can actually find the von Mises stress with some level of accuracy, even only measuring in 2 dimensions instead of 3, with a set of very reasonable assumptions. And if I plot that von Mises stress developing, that's the red is what I'm calculating as the von Mises stress. The blue is the temperature. So you see it start at 1700 C, 1700 K, should be a right axis. I apologize for that. But you see it start out in the liquid. And then as it cools, the equivalent stress starts to rise. Well, the 2 black lines there are calculations of what the yield stress would be, depending on a few different things. They sort of bound, because of course the yield stress of stainless steel depends on a lot of things other than just the fact that it's stainless steel. But that's sort of bounding levels of what the yield stress would be. And the response that you get for the von Mises stress is sort of exactly what you would expect. It's 0 until the material is actually kind of rigid, because it can't hold any stress. And then as the material gets colder and gets more and more strength, the equivalent stress rises up until it reaches a plateau. And that plateau is sort of right between the envelope of what you would expect the yield stress could be. So all this looks very nice. So even though our goal in this was really, because we're diffraction people, we're out there trying to test the technique, we are actually able to pull out some pretty relevant science about stainless steel and additive manufacturing. So let me go on from there to give you another example now. So this is, in some sense, completely different. So once you've actually AM'd the material, and I said this early on, the properties of the AM material are often very different from traditionally cast and wrought material. And I'm showing that here. This is a stress strain curve of 304L stainless steel. This is powder bed additive manufacture. The blue and red represent material that was made through parallel deposition, meaning your laser is always going like this. And crosshatch, where your laser on one layer goes 0 degrees and on the other layer goes 90. The crosshatch is obvious, maybe not obviously, but it's a much better way to make the material. But anyways, the strength parameters come out about the same. Both the powder bed additively manufactured materials are like a factor of 2 times stronger than typical wrought stainless steel. So going back to, again, how I started this, we're going to try to probe the microstructure to see why the properties are so different based on the process. So of course, you can just do ex situ microstructural things and you can get some of the answer. If you look at the microstructure of the AM compared to the wrought, you see they're very different. The 2 different sides, so up and down, are wrought versus AM, and then there's different length scales. The wrought material has a very equiaxed set of grains, and they're small. The AM material has a very tortuous set of grains, but they're in some sense quite large, but they have a lot of mosaicity to them. If you look on a smaller scale, you can see a lot of subgrain structure to the AM material that's not there in the wrought material. That certainly affects the strength. The dislocation density affects the strength. If you look at the dislocation density at the start, when the material is either in the as AM or as wrought state, we can't even detect with diffraction the dislocation density. We see in diffraction, we see dislocation density through peak width. In the wrought material, the peaks are at our instrumental resolution, so we can't even detect dislocations. That means they're probably in about the 10 to the 12, 10 to the 13 per meter squared level. In the AM material, they're an order of magnitude higher, at least. They're 2 times 10 to the 14th in the as AM material. So that also obviously affects the strength of the material. There's phases, phase difference. The wrought material shown here in red has very little or no ferrite. And I'm pointing to the ferrite peaks with the arrows. There's little or none of that in the wrought material. there's a little bit of ferrite, about 6% in the powder bed fusion material. And there's chemical segregation in the AM material. Because you go through the solidification so fast, the atoms don't get to go where they want to be. And what I'm showing you here is nickel and chromium content. You actually see high points of chromium, and that's where the ferrite is. Chromium stabilizes the ferrite. So where you have high points of chromium, you have ferrite. So all of these things could be imagined to affect the strength of the material. These are all unique features to additively manufactured microstructure that are changing the properties of the material. We did a series of in situ annealing tests in order to understand how each of those features relates to the strength. So we built a column, and by we, I mean Dave Adams at Sandia National Lab, built us a column of powder bed fusion additively manufactured material. And that's wrong. I'm sorry, I've been saying powder bed. This is directed light deposition, directed energy deposition, DED additive manufacturing. Excuse me, I made a mistake. So we built a column of that, and we cut out 6 compression samples from that column, labeled A to F. Now that's a little bit probably, this isn't a perfect experiment because we all know that AM actually as a function of height, you can get different properties. That's because at the bottom, it cools faster than at the top. And you can see that in the texture here a little bit. There's a stronger texture down here in F than there is higher solidification rate. But we're going to treat these materials, these 6 samples, as if they're all the same. That's not a perfect assumption. And we're going to heat treat them in situ. And we do it in situ so that we can watch the microstructure feature changes. So sample E, for instance, that was heat treated to 1048 K. We heated that up and we're watching the ferrite fraction change and we're watching the dislocation density change. And I'll show you in a minute that the ferrite actually goes away first. I hope I'm saying that right. In a minute, we'll know for sure. So we heated it until we saw one microfeature go away, and then we stopped. And then we tested that material without that microstructure feature. And then we took sample A, for instance, extra 150 degrees higher. So then we took a different microstructural feature out, and then we tested that material. So by doing it in situ, we could selectively pull out parts of the microstructure and see how that related to the final strength of the material. For instance, these are our peaks. This is after it's said and done. From those 6 samples, F is as built. You see how broad F is. It's hard to see because it's gray. That being very broad is due to the dislocation density. Okay. You see C, which was heat treated to the highest temperature, is quite narrow. So the width of that peak is a look into the dislocation density. And if you plot that as a function of, this is in order in terms of the heat treating temperature, you see how the peak width drops off as the temperature is increased. These solid black lines are what the peak width was to start with, and the open lines are after the heat treatment. So that change is a signal of how much dislocation annihilation, how much recovery we've had. Well, if you plot some of those features up, here you see the ferrite fraction in red as a function of temperature as you go through the 6 samples, and the dislocation density is a function in black of the temperature. And I did say it backwards early. What you see is at lower temperatures, the dislocation density goes away. The ferrite fraction persists to higher temperatures. So this is a recipe, and I'm not a material scientist, so I don't know if you'd ever want to do this. But if you wanted to get material where you annealed out all the dislocations but kept 6% ferrite, right here's a recipe for how you do that. And again, that's our mindset when we do these things. We're trying to come up with measurements that inform folks like you so you can design a process to get the final structure that you want. So this is two of the unique features of the AM material that I described. Another one was the grain morphology, right? So in the as AM material, sample F up on top, you see that tortuous microstructure. And as you heat treat it higher and higher, by A, the size scale maybe has changed. That might more be A, B, C, D, E, the position that it was grown. I don't know. Oh, okay. Well, I took it off of my screen. I don't know if I can get it off of that. Well, we're almost done. C, you can see complete recrystallization. Okay, so by going to 1500 Kelvin, we've now changed the grain morphology. So that's another microstructural feature that we took out. And then finally, that chemical heterogeneity that I told you, that drops out between, well, 1000 K and 1100 K. You see it starts out with the areas of chromium, reduces a little bit in the lowest temperature sample, and these are rather time consuming, so we didn't get to do it for every sample. But you can see now up about 1200 K, that chemical segregation has gone away. So now I've shown you different temperature regimes where you can take out first dislocation density, second ferrite segregation, and fourth grain homogeneity. And that's what this chart is trying to show, is the 6 samples that we've created by taking out one at a time the different microstructural features. And then we take those samples and deform them again and look at the strength of them. That allows us to basically assign strength to feature. So this is the result of a in situ compression test. So if you could see the left-hand side, that's the strength of the material as a function of dislocation density, right? This is the Taylor law. Taylor would tell us that the strength of the material should go as the square root of the dislocation density. So if you look at the as-built material, it has a certain strength and it has a certain dislocation density. As you strain it and it work hardens, the dislocation density goes up, the strength goes up, you get a proportionality. Again, that's the Taylor law. And you get a nice line here. If you blow that up and look at the different heat-treated materials, this is the same line, but now, and you can't quite see F, F is up and to the right, but these are the different samples that have been heat-treated at different temperatures and how their strength affects, or strength is related to the dislocation density. So samples B, E, D, and A, you see a nice linear progression. Oh, there we go. So you see a nice linear drop. So all of that strength is related to the decrease in dislocation density with heat treating. Now, you might not remember the nomenclature of the samples, but sample A, for instance, didn't have any ferrite left in it. What this is really saying is the ferrite didn't affect the strength. Up to sample A, everything's being controlled by the dislocation density. Sample C, remember, recrystallized. So that's where we change the grain morphology. C is below the Taylor curve, right? So that's giving you the amount of the strength that's related to the grain morphology. So essentially, this is allowing us to separate the strength into this part's due to dislocation density, this part's due to grain morphology, and the ferrite doesn't really have any effect at all in the strength. Yeah, okay, a little more illustrations. So at that point, I'll wrap up. Actually, not too bad on time. So what I tried to show you, first and foremost, my message, because I'm a diffraction person, is that X-ray and neutron diffraction is a window onto pulling out microstructural features from your material. And because it's non-destructive, and depending on your kinetic, it can be real time, it can be used to monitor how your microstructure evolves during processing, during deformation, during performance, all those sorts of things. If you can simulate the environment, then you can watch the microstructure evolve while your sample's in that environment. X-ray measurements can be used to monitor very fast processes. What I showed you was at 1 hertz. Today, you can certainly do 200 kilohertz, maybe 500 kilohertz. You can do individual measurements very fast at, again, the femtosecond time scale, but you only get one measurement at that time scale. You can't do a series of them. Neutrons, on the other hand, are very slow. That doesn't mean they don't give you information. You want to match the kinetics of the science you're doing to the experiment that you're doing. And again, when we're doing our job right, the data that we collect is being fed directly to modelers, right? For me to know the ferrite fraction as a function of temperature in steel, all right, that's interesting. I can write a nice paper, but it really doesn't help anybody. For me to feed that somebody that can then develop a model and predict these things and design a process based on that data, that's when we're doing our job well. And that's really our goal as material scientists. Right? At that point, I'll stop and take any questions. Yeah.
So for the process where you were measuring kind of away from the melt pool slowly,
Yes.
I imagine that if you're spinning the wheel,
Yes.
on a video instead of mission,
Yes.
that would be slightly moving away, but that means the wheel's spinning this way, and then your entire deposition system is spinning the other way. As deposition continues.
So what we actually did, and that is what we did to get the measurement as a function of distances. The
Okay.
wheel spun,
Yeah.
so you could sit for a set amount of time at one spot. And again, that's sort of quasi steady state.
Right.
And then we translated the wheel so
Okay.
that we moved back. But
So
the
what's
translation, yeah, the translation was slow enough that it says in each point, you're measuring steady state at that point.
And the diameter is wide enough, you can basically assume you're maintaining a constant radius.
Well, so I didn't go into it, but in the picture, it was actually showing the scale, right? The curvature was the real curvature relative to everything else. So yes, we did move a not insignificant amount further from the base plate
Okay,
as it rotated away. That was poor choice of design. There was, the idea of making a wheel was so you could do an infinite time. In reality, the most we ever did was, well, at that time, again, detector limitation, you could only do 240 of those images at a time
right.
before the detector ran out of memory. So that limited you to 6 minutes. So you couldn't quite do a full rotation.
So it's a- right.
It would have been a little bit more simple, but
Okay.
yeah,
And
we
then,
learned. Yeah, we were testing the technique, so.
yeah, one of the questions that, ultrasonic fatigue, specifically vibrational modes, whether your specimen is vibrating in one mode or multiple,
Yes.
kind of what the relationship between those modes are.
Yes,
If this can measure at a very high rate and it can measure strain tension,
yes.
then conceivably I could in one mode or multiple, and what the relationship or the I guess the scale between those modes is.
Yes.
So that would be
So I'm guessing if you're at ultrasonic, you're probably at rates that are going to be
20
difficult.
kilohertz.
Yeah, so there are detectors that measure faster than this. And again, I didn't go into this level of detail because you guys aren't instrument scientists. But you can measure faster, but you sacrifice certain things. In order for me to separate temperature from stress, I need to measure that full ring. That means I have to have a big detector, and that's what makes that detector slow.
Right.
There are detectors out there that'll measure megahertz, but they're tiny little detectors and they'll only measure a fraction of that ring.
I see.
So then you can no longer do that separation of the microstructural features.
So one of the ways that you get around that usually multiple images of it over several cycles at the same exact point in the
Yes.
cycle,
Yep.
construct
Yep.
the whole,
Yep.
idea of what's going on at that point, and then it's
Yep.
several cycles.
And that's
Or take it at a
exactly-
different point in the cycle on the
Yep.
T cycle.
That's exactly where I was going to go. Those are called stroboscopic.
Yep.
Right? So it's just like a strobe light. If you've ever been dancing in a strobe light, you do the exact same thing. It's hard to do. With the x-rays, you can do it at a fixed rate. It's just the nature of how they make the electron beam that creates the x-rays is pulsed,
Okay.
right? It's not a continuous beam. And I don't remember, I don't know if you remember, Dan, it's 100 nanoseconds or some microseconds between pulses. So if you're measuring things on those rates, you can get a diffraction pattern from a single pulse.
Mhm.
And you could tune your ultrasonic part to match that rate. Yeah, exactly. Or, if your period is much slower than that, then you can do it electronically, right? You can only bin the data over certain timeframes.
Yeah.
So there are various stroboscopic methods to do exactly what you're saying. I haven't heard of it being done for ultrasonics. In a way, we've done that during shocks, right? So I mentioned the linear coherent light source where you measure for the X-ray pulse is only 80 femtoseconds long, but you only get one of those every couple of seconds. So you have one sample, you hit it with a laser that drives a shock to it, you wait about, say, 4 nanoseconds, and then you shine it with the X-rays and you measure the state 4 nanoseconds after the pulse hit it. Then you move another sample into position and you do the same thing, but you measure it 5 nanoseconds later.
Yeah.
And assuming that your pulses are all the same, which is true, because the pulses, lasers work that way. And assuming your samples are all the same, which isn't true, because samples work that way, then you can develop a time evolution of the process, and you can see the wave. In this case, we were looking at a stress-induced phase transformation or pressure-induced phase transformation, and you can see the wave of transformation through it. So there are ways to do that. One of the things, it's an idea I have, but this isn't of interest to Los Alamos, so I haven't explored it. Ultra-fast laser machining of hard ceramics, right? You hit boron nitride or diamond ablation, with some sort of laser beam for femtosecond resolution. You could absolutely do that and watch how that pulse, watch it ablate away material and watch the recoil through through what you're cutting, yeah. If you wanted to better understand the physics of that type of machining, that's something you could do with the linear coherent light source. If that was, if that's of interest. But that's the way X-rays are going, is to very fast processes, because the X-ray sources are increasing in flux at a rate that's unbelievable.
Yeah, and the something like just that, every cycle is identical except for that slight deformation.
Yes, and especially if you're doing frequency.
Yeah, you're limiting a lot of confounding variables, focusing on one thing changing constantly. Like you said, whenever you're changing temperature, you're changing.
So they certainly do that in a fatigue test sort of way, where you might be doing 1 cycle per second. Ultrasonics is just the same thing. I'm sure it's
for us, one end on constraints. We have to always worry whether that odd end is resonating perfectly linearly or slightly out of focus.
Yeah, I think you can do that.
So right now you talked about, you focus your beam spot, and you've always got to move the specimen in order to understand anything about spatial differences.
Yes.
Has the leisure focus, the fact that the detector is so static, you have to have the beam in the same location.
Well, so I mean, there's a lot of parts to that question. One, it's hard to move the beam.
Yeah.
And so the beam comes out white, and you go through a monochromator system.
Okay.
So actually, I take it back. It's really easy to move the beam. If you shift the monochromator, then it's like a lighthouse.
Yeah.
But as you do that, you would be dynamically changing the properties of the beam. So your calibration would go to crap.
Okay.
Same with the detector. The calibration of the detector is dependent on where the beam is. Now, if you knew where the beam was moving, you could correct that. But in general, it's a lot easier to move the sample than it is the beam. Turning the synchrotron on its side is a problem. But yeah, you can scan it in the direction of the monochromator, but you would never want to do that. They spend a lot of energy trying to keep the beam from not moving, because the monochromator heats up and stuff like that. And the very first synchrotron they built, they put the monochromator on there, they turned it on. The first thing that happened is the monochromator exploded. The heat density of the white beam before it's monochromated is greater than that of the surface of the sun. So cooling the monochromators became a very important thing very quickly, because they couldn't take the heat load. And that's something they still battle with. They have to have active feedback in order to keep things aligned. So keeping the beam from drifting is the biggest problem. So nobody does it. No, that's just for how you steer the electrons.
Okay.
That's a need for getting electrons around in a circle, and how you accelerate them.
Very much again.
Thanks a lot for your attention. Thanks again for the invitation.
That is the importance of it.